Let's start by just considering these three variables: the person's gender, how old they were when they won the award, and the award year. So we're going to need to summarize each of these. Gender is categorical. We would be having a count and a percentage of males and females. This group is fixed that it's half and half, so it's not going to be particularly interesting. We've already done a summary of the age at award. We've looked at the overall average age of the award. And the new variable we have is award year. Again, this is a fixed variable where there are two every year, except for a few outstanding ones where there were multiple ceremonies in a year. So not particularly interesting to do a descriptive summary of award year. So let's consider the relationships between two variables, one predictor, one outcome. Let's consider those. So does gender predict age at award? Oh, hey, we've already done that, right? We've considered that. Is gender and award year, are those related? Is that an interesting comparison? Let's think about that. Every year, one man and one woman is chosen as the best actor and the best actress. So it's not variable. It's a fixed constant that there's one man and one woman every year. So that's not really going to be a very interesting comparison to make. And then the final one is age at award related to award year? So as the award years have progressed, has the age at award changed? Now, while we're looking at this, we're thinking that gender is only a predictor. Neither age at award nor award year is going to predict gender. The age at award, that's only going to be an outcome. That, what does predict age at award? Does the award year predict age at award? Does gender predict age at award? So really that arrow should be facing the other direction. It's just showing that those two, we need to consider those two together. And then finally, award year, well, that's really just a predictor, isn't it? So does award year predict age? It's a good idea to map them out and to consider all of these comparisons that you could make. Remember to be clear about if there is a predictor and an outcome, if there's a time sequence, if the predictor always would come before the outcome, or if there's a logical or theoretical reason why one variable would predict another. And otherwise, you can also just include these two variables are related and I'm not quite sure whether one's a predictor and one's an outcome. So we're asking the question, has the age of the winners changed over the years? Does the year of the award predict the age of the winner? Our predictor variable, year of the award, that's continuous. Those are numbers along a scale. Our outcome variable, age in years, that's continuous. They're numbers along a scale. So we have a continuous predictor variable and a continuous outcome variable. We're going to look at an XY scatter plot and we're going to calculate a correlation coefficient. There are no groups. Neither of those is categorical. Before we were calculating means of groups and doing a means comparison, but this time we don't have groups. They're both continuous. The predictor variable is clearly the year of the award, whether that predicts the age. So let's start just by putting the two variables we're interested in, year of award and age in years, in contiguous columns. So I'm just going to highlight column H and copy and paste it here. So we've got in K and L, the two variables that we're interested in. What we're going to do is we're going to copy those and upload them into SEEIT. We're going to use a different area of SEEIT, a different tool in SEEIT. I've highlighted K and L. I'm going to use the Command C to copy those. And then I'm going to jump to SEEIT. So I'm coming to SEEIT 3 Correlations version 3. The previous tool we were using was distributions and this one's correlations. It's going to look very similar to begin with. We're used to seeing our data sets. We're going to add our own data set. It's on our clipboard, right? The blue is showing us that that's highlighted, so we just Command V to paste our data. I think because I highlighted the whole column, I pasted a whole bunch of blank spaces under it as well. Oh, but there it is. There's our year of award and age at award. I'm going to go ahead and edit the title here. I'm going to use the title Age at Award by Year. So that's my outcome by my predictor, first column is not a label, the first column is data. We're going to load that worksheet from the form. And there's our data added to the data sets. I'm going to start by dragging my predictor variable over to the x-axis. As predicted, the year of the award has been pretty constant. That there have been, for the most part, 2 awards every year. And now we're going to drag our predictor variable, and now we're going to drag our outcome variable, the age at award, to the y-axis. And each one of these represents one of the actors or actresses. So this one here is the year 1932, and the age was 47.6. So in 1932, one of the actors or actresses was 47 years old, 47.6 years old. So we can see each member of our population laid out in that XY scatter plot. A scatter plot like this is showing the relative location of each participant on 2 continuous variables. So this dot here is showing that in 1961, one of the winners was 47.5 years old. So it's showing the relative position both on the x-axis and on the y-axis. Can you see much of a pattern here? It seems like it's maybe increasing if we were to look at the line, the general trend of those, but it's a little bit hard to see it here. Do you see the cluster of older winners? It looks like between 82 and 90, we had our 3 oldest winners all very tightly clustered together in less than 10 years, or in an 8-year span. When we're identifying a relationship between 2 continuous variables, we want to consider 2 things. The first one is the nature of the relationship, whether there is a relationship, and if there is a relationship, if that's a positive relationship or a negative relationship. We do this by identifying what's called the line of best fit. So what we're going to do is imagine and then draw a line that fits this data best. And what that means is a single straight line that minimizes the distance of each of the participants to that line. See, it really allows us to play with this idea. We're going to start by trying to draw it on our own. So we're going to click on the wrench and let's say draw, and it says, so under draw, we're going to choose that show line, the red show line. So it's just put a line right there, straight across the middle. And along the top, it says sum of squares equals 39,660. Okay, we want to play with this and see if we can get that number, see how small we can get that number. I'm going to start by clicking in the middle of the line and pulling it down. Do you see how as I put the line closer to the bulk of the data, the sum of squares is going down? So let's keep moving it down until it's as little as it can be, going just up and down. I think somewhere right around there. Now let's angle them. So if we angle that up, it goes up. If we angle it down, it seems like I was getting it down a little bit further. How about if we pull this side up? Yes, the line is still going, the number is still going down. So I've got it down to 20,900. That seems to be about as good as I can get. How did you do that? What choices did you make? When we say line of best fit, I want you to imagine each one of these spots has a line that is absolutely straight up and down, vertical, dropping from that point to the line. And so how far away each point is from the line. This spot is right on the line. It's no distance at all. And so what we're trying to do is minimize the overall sum of those distances. We added up how far away each of these participants is from the line. The line of best fit would have the smallest overall total sum of those distances. Some of those participants are above the line. If we were to take 50 and minus 40, what is that? Probably 42, we'd get a positive 8. Some of those participants are below the line. If we were to take, what's that? 33 and minus 42, we'd get a negative number. So we're going to need to have a way of making sure that all of those numbers are positive, and otherwise they just cancel each other out. I'm sure you can think of two ways of making a group of numbers, half of which are positive and half of which are negative, all the same sign. You could talk about taking their absolute value. That would be one way of doing it. But those darn statisticians, they decided to square those numbers instead. So we're going to take each of those distances from the line and we're going to square it, and then we're going to add up those squares. And that's where we come up with this word, this phrase, sum of squares. Now, so if this point is 2 years above the line, to square it is to times 2 by 2. And it's very literally to make a square. So instead of just a line, we can square it. We can make a square. And that's very literally what that sum of squares means, is if we were to draw not just lines from each participant down to the line of best fit, but were to draw a square that included the participant at one corner and the line of best fit at one corner, and then added together these areas of those squares. Do you want to see them? It's going to look a little bit crazy on this data set because there's so many participants, but see, it allows us to show those. So we can show the squares. Do you see them? So here is that participant. There is the line dropping down to the line of best fit. And there is the remainder of that square. And we're going to be, and then this sum of squares number is adding up all of those squares. And so if I move that, if I move it up, I'm minimizing and making really little squares above the line, but I'm making lots of huge squares below the line. And as I move that down, they're more equally distributed above and below the line. But that's pretty messy with this many data sets. Let's have Siet calculate the actual line of best fit. Under that wrench, instead of drawing our own line, well, we're going to leave that there, but we're going to come over here to where it says least squares. And I'm going to click on that green, show the line. There's the line that is the mathematically smallest, least sum of squares. How close did you get? Did you get pretty close to that? I'm going to go ahead and turn off the one that I drew. And I'm going to ask to show the R value and the sum of squares. So it got the sum of squares down to 20,927. What does that mean? Let's talk a little bit about our visual reasoning with the nature of the relationship. We've also got a correlation coefficient here, the letter R, equals 0.16. So what does that line of best fit tell us? Let's use our visual reasoning skills and think about that for a second. If the line of best fit has a positive slope, if it is increasing from left to right, that means that there is a positive relationship between these two variables, that as the predictor variable increases, so does the outcome variable. As the predictor variable decreases, so does the outcome variable. They go up together and they go down together. If that line had a negative slope, then we would be looking at a negative relationship, that as the predictor variable increases, the outcome variable decreases. And as the predictor variable decreases, the outcome variable increases. With a negative line of best fit, we would look at that and see that as one increases, the other decreases. They go up and down, opposite of each other. The other thing that we consider when we are looking at the relationship between two continuous variables is the strength of that relationship. To consider the strength of the relationship, we can look at this XY scatter plot and think about how closely, how tightly do those data points cluster around that line of best fit. Are they very, very tightly clustered around that line? Or are they quite spread out around that line? And we're going to refer to this as the strength of the relationship. Let's take a look and see how we can think about this. So we're going to go back and draw our own to begin with. So let's put up an ellipse. And the game here is to draw the smallest shape you can that has 95% of the observations inside of it. So you want to capture 95% of the observations. You can change the location, you can change the size, and you can change the rotation. So you've got 4 hot buttons on the edges and 1 in the middle. So as you see at the bottom here, it's got a number of points inside. I've got up to 115 here. What did I say? We wanted to have 95%. There are 176 observations in this group. 95% of that, you would calculate that by doing 0.95 times 176 is 167. So you want this number to get up to 167 and it to be the smallest shape you can that achieves that. So let's see, I need to capture a few more here. Oh, that's 157, that's not going to do it. It looks like I'm really going to need to capture that little cluster there, this little cluster over here. How can I do that? That's 165, 168. Oh, good, we've got it. Ah. That's the shape that I came up with in order to capture 167 of those observations. What did you draw? So let's think about our visual reasoning skills when it comes to the strength of the relationship. We're asking how tightly clustered are these around the line of best fit? And in this example, they're not particularly tightly clustered. We needed to draw quite a big shape in order to capture them all, or to capture 95% of them. However, there is a definite pattern. Here's the rule with this visual reasoning task. If the shape you ended up with was pretty much round, that means there's no relationship at all. If the shape you ended up with looks like an American football, that means that there's likely to be a weak relationship. And if the shape that you ended up with looks like a surfboard, then that would indicate a strong relationship. I'm going to say that this is between round and a football. A surfboard would be more like that. If we had a surfboard around the line of best fit, and if 95% of the observations fell within there, we would be looking at a strong relationship. But we don't really have a surfboard. We've got more of a football. I predict that we're going to discover that this is a weak, positive relationship, that it increases from left to right, and that it's weak, it's relatively spread out.